Hello and welcome back to my channel, as it were, and today we're going to be looking at an interesting geometry problem. So we're asked to show that the green area in the question is equal to r squared times pi theta minus 180 over 360. So first of all, we are going to draw in this section of the circle, and we're going to label this length r, and this length is also r, because they're radii of the circle. I'm going to label this angle as theta, simply because that's the angle used in the question. I'm going to posit at this point that theta is equal to 90 degrees, but I have no proof of that. I'm just going to hope that it is, and if it isn't, I'll have to work around that. So, next step, how are we going to work out the green area? So I'm going to work out, I've drawn that on, and what I'm going to do is I'm going to calculate that area, which will be theta over 360 times the area of the circle, which is just pi r squared, minus the area of the triangle, which will be half r squared times sine of theta. We don't know what theta is, but if we could know theta, then we would be able to find out if that will give us our minus our 180 over 360. Right. So, what are we going to do next? We are going to label our diagram again. So what we are going to label with are these two lines, which are both radii, but you'll notice that they're connected to tangents, and this means that they're at 90 degrees using circle theorems. And this means we have a square. So this length is r, and this length is also r. And what that allows us to do is find this diagonal length, because ultimately we want to find the side length of the circle, which I'm going to call S, and so this length is S minus R, and this is also S minus R. And we want to find S. So we need to find this diagonal here, and then add it to R, and then use Pythagoras Theorem to find our side length. Okay, I'm going to draw this triangle in. That triangle will look something like this. It's just a right-angled triangle, and it has side length r at these points, and this length will be r root 2, because if you remember, if you have a square that's halved to make a triangle, and its side length is 1, then you have a root 2 diagonal hypotenuse here. And also, were these numbers to be replaced as a, then it would be a root 2, just as we have here as r root 2. So now we know that the diagonal of the circle, not circle, square, the diagonal of the square is equal to r root 2 plus 1. And what we're going to do with this is we're going to say, using Pythagoras Theorem, that 2s squared is equal to r squared root 2 plus 1 squared. And then we're going to divide both sides by 2 and square root. So s is equal to I'm not saying plus or minus, because in Pythagoras Theorem you can't have negative lengths. And also, I don't want to create any new solutions. So what we're going to do is we're going to divide by 2 and square root. So we have s is equal to r times root 2 plus 1 all over root 2. And now we're going to rationalise the denominator and say that s is equal to r times 2 plus root 2 over 2. And this 2 here will cancel, and we're just left with that we're just left with s is equal to r times root 2 plus 1. We now have the side length of the square. How does this help us? So what we need to find now is we need to find what the length s minus r is. So we do the side length s, which is root 2 plus 1 times r, minus r. And we have this little plus 1 here, which is multiplied by r, and we're minusing r, so these two values can cancel. So now we know that s minus r is just equal to r root 2. Shouldn't that be over 2? Over 2. Sorry. R root 2 over 2. That's just because I forgot to put in the divided by 2, because when I cancelled here, I shouldn't have removed the 2. So that's got divided by 2. So I now have r times root 2 over 2 as my s minus r. And what I'm going to do now is I'm going to address this, that I posited that it was 90 degrees. So I'm going to draw a line up here, and because it's perpendicular, I know it's 90 degrees. And I know, because this length is r, and this length is s minus r, and this is also s minus r, that this angle will be 45 degrees, and this angle will be 45 degrees, because it's an isosceles triangle. I also know that if I drop a perpendicular here, that this will be 45 degrees, because two 45 degrees make a 90 degree angle in this square. And then, because I know that these two lengths are the same, so we have a side length r and another side length r of this big triangle, I know that the other angle of theta is 45 degrees. So theta is 2 times 45 degrees, which is equal to 90. So I know that theta is equal to 90 degrees. Well, that helps a lot. So what I'm going to do now is I'm going to say that the triangle's area is equal to, just ignore the fact I've drawn a triangle. I've drawn a triangle because it's just symbolising the area. Sometimes a triangle is used to denote the discriminant of a quadratic equation, or even a cubic equation, as I've shown in my polynomial series. So, half AB sine C. Well, A is equal to R, which is equal to B, and sine C is equal to sine of 90, which is just equal to 1. So therefore, half AB sine C is just equal to half r squared times sine 90, but we can take that out because we know it's just 1. So we have the area of our triangle. And what we're going to do now is we're going to run back to the original thing I mentioned, that in order to find the area of that little segment, we do pi r squared times theta over 360, and we minus r squared over 2, which is the area of the triangle. If I take a factor out of r squared, that will give r squared multiplied by pi theta over 360 minus a half. And if I get a common denominator here, that will give r squared times pi theta minus 180 all over 360 shown. Thank you very much for attending this episode, and I look forward to seeing you all next time.